The young woman held the flashlight steady, its beam revealing what her eyes alone could never see. Inside the aluminum tubing, barely visible even with the light, were scratches. Not the random marks of careless handling, but uniform grooves running lengthwise, as if something had scored the soft metal with methodical precision. She marked the tube with chalk and set it aside. Another defect. The fifth one that hour. It was November 1942 at the Willow Run bomber plant, 35 miles west of Detroit. The woman was one of dozens of quality inspectors working the day shift, examining the thousands of separate tubing pieces that would compose the fuel, hydraulic, de-icing, and other critical systems in a B-24 Liberator bomber. Each inspector had been trained to look for specific defects, cracks, improper welds, dimensional errors, contamination. But lately, they were finding something else. Damage to the aluminum itself. Scratches, gouges, and deformations that shouldn't exist on brand new parts fresh from the forming machines. The inspectors reported their findings. Supervisors examined the rejected parts. Engineers were called in to investigate. What they discovered would expose a fundamental miscalculation that threatened to derail America's entire heavy bomber production effort. The problem wasn't sabotage. It wasn't worker incompetence. It was something far more troubling. Ford Motor Company, the most advanced manufacturing operation in the world, had applied its legendary automotive production methods to aircraft manufacturing without understanding that aluminum and steel required fundamentally different approaches. The hard steel dies that stamped car parts into shape with perfect efficiency were destroying the soft aluminum components that comprised 85% of a B-24 Liberator. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments what other untold moments from the war you'd like to hear about. By the time the full scope of the problem became clear, Ford had built 56 B-24 bombers in 1942. Every single one was deemed unfit for combat. They would be relegated to training bases, reconnaissance patrols, and transport duties. Never combat. The dies and machine tools representing millions of dollars in investment would have to be thrown out and completely redesigned. Critics who had doubted Ford's ability to mass-produce heavy bombers seized on the failure. The press began calling Willow Run Will It Run with barely concealed mockery. Senator Harry Truman, heading a congressional committee charged with investigating waste in war production, arrived at the plant with what one observer called blood in his eye. The arsenal of democracy, America's bold promise to overwhelm the Axis powers through sheer industrial might, was producing bombers that couldn't fight. The story of how this happened begins not with failure but with supreme confidence. Ford Motor Company in 1941 was the most successful manufacturing enterprise in human history. Henry Ford had revolutionized industrial production with the moving assembly line. His River Rouge complex in Dearborn, Michigan, was a vertical integration marvel spanning 2,000 acres. Raw materials entered one end. Finished automobiles drove out the other. Iron ore from Ford-owned mines arrived by Ford-owned ships. Ford-owned coal mines provided fuel. Ford-owned rubber plantations supplied tires. The company smelted its own steel, generated its own electricity, made its own glass, and produced virtually every component that went into a Ford vehicle. The production efficiency was legendary. In 1936, Ford could take raw iron ore and transform it into a complete automobile in 41 hours. The Model T, which had once taken 12 hours to assemble, rolled off the line every 93 minutes by 1913. By the 1920s, Ford's Highland Park plant could produce a Model T in just 93 minutes, with a single plant churning out over 1 million vehicles per year. The company's mastery of mass production had made automobiles affordable to ordinary Americans and had turned the United States into the world's leading industrial power. This confidence in mass production methods was not unfounded. Ford's techniques had been studied, copied, and adapted by manufacturers worldwide. The Soviet Union's massive Gorky automobile plant was modeled directly on Ford's River Rouge complex. Nazi Germany's Volkswagen plant employed Ford-inspired production methods. When the United States entered World War II, It was natural that government planners looked to America's automotive industry to produce the vast quantities of military equipment that would be needed to fight a global war. Aircraft, tanks, artillery, trucks, jeeps, the American military would need them all in unprecedented numbers. And if anyone could produce them, it was the automotive manufacturers who had perfected mass production over decades of experience. The challenge came on May 26, 1940, when President Franklin Roosevelt delivered a fireside chat that stunned millions of listeners. "I should like to see this nation geared up to the ability to turn out at least 50,000 airplanes a year," Roosevelt announced. 50,000 combat aircraft within 12 months. The goal exceeded the total number of all planes built in the United States since the Wright brothers' flight at Kitty Hawk in 1903. As Roosevelt spoke, the country had fewer than 3,000 military aircraft, most obsolete. The aviation industry, accustomed to handcrafting planes in relatively small numbers, was completely unprepared for production on this scale. Roosevelt and his advisors believed that long-range, high-altitude heavy bombers would be the decisive weapon in the coming war. The B-17 Flying Fortress, developed by Boeing, had already proven itself in early combat operations in Europe. But even more capable was the consolidated B-24 Liberator, a twin-finned, high-winged heavy bomber with dual bomb bays and impressive range. The B-24 could fly farther, carry more bombs, and operate at higher altitudes than most contemporary aircraft. It was also more complex than any plane ever designed for mass production. 67 feet long, the B-24 contained 450,000 individual parts and 360,000 rivets in 550 different sizes. A single B-24 weighed 18 tons. By comparison, a typical automobile of the era had 15,000 parts and weighed about 3,000 pounds. Consolidated Aircraft in San Diego, California, had designed the B-24, but the company lacked the facilities and production capacity to build bombers in the quantities the military required. Consolidated's methods were traditional aircraft manufacturing, skilled craftsmen building planes largely by hand, each aircraft essentially custom-made using jigs and temporary fixtures. It was excellent for producing high-quality aircraft in modest numbers but completely inadequate for the scale of production Roosevelt demanded. The government needed someone who could apply industrial mass production techniques to heavy bomber manufacturing. They needed Ford. Charles Sorensen, Henry Ford's right-hand man and production chief, visited Consolidated's San Diego facility in January 1941 to assess the operation. What he saw shocked him. Workers were building aluminum airplanes outdoors on steel fixtures. Components were handcrafted to fit each individual aircraft. There were no interchangeable parts, no standardized assemblies, no moving assembly line. Everything Sorensen knew about efficient production was absent. They were, he would later recall, building airplanes the way we built cars in 1908. But Sorensen saw opportunity. If Ford could apply its automotive production methods to aircraft manufacturing, the company could revolutionize bomber production. Sorensen believed Ford could build B-24s on a moving assembly line with standardized, interchangeable components. He proposed building not just some B-24 components but complete aircraft, hundreds per month, rolling off the line with the same efficiency that produced Ford automobiles. The Army Air Forces, desperate for bombers, eagerly accepted the proposal. In February 1941, contracts were signed. Ford would build a massive new plant dedicated to B-24 production. And Sorensen made a bold promise: Willow Run would produce one B-24 bomber every hour. 60 aircraft per day. 1,800 per month. The claim seemed impossibly ambitious even by Ford's standards. Aviation industry leaders were openly skeptical. "You can't expect a blacksmith to make a watch overnight," scoffed Dutch Kindleberger, president of North American Aviation. Others pointed out that aircraft required precision and quality control far beyond automotive manufacturing. A car with a minor defect might break down on the road. An aircraft with the same defect could kill its crew and fail its mission. The tolerances were tighter, the consequences of failure more severe, and the complexity vastly greater than anything automotive manufacturers had attempted. But Ford pressed ahead with characteristic confidence. The company selected a site on farmland Henry Ford personally owned near the village of Ypsilanti, 35 miles west of Detroit. Architect Albert Kahn, who had designed Ford's River Rouge complex, was commissioned to create what he boasted would be the most enormous room in the history of man. The specifications were staggering: 3.5 million square feet of factory space under a single roof. An aircraft assembly line over a mile long, with a massive turntable that could rotate partially assembled B-24s 90 degrees to move them through different production stages. 6 runways and 3 aircraft hangars on adjacent property where completed bombers would be tested and prepared for delivery. At peak capacity, the plant would employ over 100,000 workers. Construction began in April 1941. Concrete was poured continuously, day and night. Steel frameworks rose across the flat farmland. Within months, the massive structure took shape. It was, as promised, the largest factory building in the world, stretching so far that workers on one end could barely see the other. Ford equipped Willow Run with the latest production machinery, much of it designed specifically for this project. Die-making facilities could produce the steel dies needed to stamp metal components into shape. Machine shops could manufacture the fixtures, jigs, and tools required for precision assembly. Testing equipment would verify that every component met specifications. The plant had its own power generation, its own water supply, its own fire department. It was, in essence, a complete city dedicated to one purpose: building B-24 Liberators. The plant's official dedication ceremony on October 22, 1941, drew Major Jimmy Doolittle of the United States Army Air Forces, who would later become famous for leading the first bombing raid on Tokyo. Doolittle praised Ford's commitment and expressed confidence that Willow Run would make a decisive contribution to America's military preparedness. Henry Ford himself, though officially retired, attended the ceremony. At 78 years old, Ford represented American industrial achievement. He had transformed manufacturing, created the middle class through high wages, and proven that American ingenuity could solve any production challenge. If Ford said Willow Run would produce a bomber an hour, skeptics were hesitant to bet against him. Production officially began in the summer of 1941. Workers, many hired from Detroit's automotive plants, arrived for training on aircraft assembly. The differences from automotive work quickly became apparent. Aircraft components required precision measured in thousandths of an inch. Assembly procedures were more complex, with multiple steps that had to be performed in exact sequence. And unlike cars, where a single worker might install the same component on vehicle after vehicle, aircraft assembly required teams working together on large sub-assemblies that were then integrated into the final aircraft. But Ford's managers remained confident. They had scaled up automotive production before. They had trained thousands of workers on complex assembly procedures. They had solved countless production challenges through engineering and process improvement. Aircraft manufacturing might be more complex than automotive production, but the fundamental principles were the same: break the work into simple, repeatable steps, standardize components, create efficient material flow, minimize wasted motion, and drive toward continuous improvement. The Ford production system, refined over decades, would triumph over the traditional, inefficient methods used by aircraft manufacturers. The tooling was the key. Ford invested heavily in dies, fixtures, and machine tools specifically designed for B-24 production. For automotive manufacturing, Ford used hardened steel dies that could stamp sheet metal parts with tremendous force, creating precise shapes quickly and reliably. These dies lasted for millions of cycles and produced parts with consistent dimensions. The same approach, Ford's engineers reasoned, would work for aircraft components. They specified hard steel dies for stamping the aluminum parts that would comprise the B-24's structure, skin, and internal components. This decision seemed entirely logical. Steel was stronger than aluminum, obviously. Hard steel dies had proven themselves in automotive production. And Ford's die-making capabilities were second to none. The company's die shops could produce complex, multi-stage dies that formed intricate shapes with minimal waste. These dies were engineering marvels, representing decades of accumulated knowledge about metal forming, tool steel metallurgy, and production efficiency. Using these proven dies for aircraft production seemed not just reasonable but obvious. No one at Ford in those early months seriously questioned this approach. The company's engineers had designed automobiles for decades. They understood metal forming, stamping, and fabrication better than almost anyone in the world. Aircraft manufacturers might handcraft their components with softer dies and more manual labor, but Ford would bring modern mass production methods to the industry. Hard steel dies would stamp out B-24 components with the same efficiency that produced car parts. And if the aircraft manufacturers warned that this wouldn't work, well, they were protecting their outdated methods against Ford's superior technology. The first components came off the Willow Run production line in November 1941. Initially, Ford was only contracted to produce B-24 parts that would be shipped to Consolidated in San Diego or Douglas Aircraft in Oklahoma for final assembly. But by October 1941, Ford had negotiated permission to assemble complete B-24s at Willow Run. This required even more sophisticated tooling and assembly procedures. Ford's engineers designed assembly fixtures for the B-24's major subassemblies: wings, fuselage, tail section, and bomb bay. Each fixture had to hold components precisely in position while workers installed fasteners, sealed joints, and integrated systems. The dies went into service. Sheet aluminum moved through the stamping presses. Components began accumulating in inventory. Assembly work proceeded. Workers learned their tasks. Supervisors managed production flow. The massive assembly line began operating, moving partially completed structures through station after station. From the outside, Willow Run appeared to be fulfilling its promise. The largest aircraft factory in the world was producing B-24 components on an unprecedented scale. The arsenal of democracy was becoming reality. But the quality inspectors, including the young woman with the flashlight examining tubing for defects, were beginning to find problems. Small at first. A few scratched components here and there. Some dimensional variations. Minor deformations that might be within acceptable tolerances but seemed more common than expected. The inspectors did their jobs, marking defective parts for rework or rejection. But as production ramped up through the late months of 1941 and into early 1942, the defect rate didn't decrease. If anything, it increased. More scratched aluminum. More gouged surfaces. More components that didn't quite meet specifications. And then came the first assembled aircraft. The first B-24 Liberator, built entirely at Willow Run, rolled off the assembly line in September 1942, nearly a year behind schedule. It should have been a triumph. Instead, it was the beginning of a reckoning. Because when Army Air Force's inspectors examined that first bomber, and the 55 that followed it during the final months of 1942, they found what the quality inspectors at Willow Run had been reporting for months. The aluminum was damaged. Not catastrophically. Not obviously visible to casual inspection. But present throughout the aircraft in ways that compromised structural integrity, created stress concentrations, and reduced the safety margins that meant the difference between an aircraft that could withstand combat damage and one that would fail under stress. The Army rejected every single one of the 56 B-24s Ford produced in 1942 for combat operations. They were assigned instead to training bases, where students could learn on them without the risk of combat. They could fly reconnaissance missions over safe territory. They could serve as transports. But they would not carry bombs over Germany or Japan. They would not face enemy fighters or anti-aircraft fire. Because the Army Air Forces had determined they simply weren't safe enough for combat. Charles Sorensen had promised 1 bomber per hour. Ford had delivered 56 unfit bombers in an entire year. The critics had been right. The blacksmith couldn't make a watch overnight. And somewhere in the massive expanse of Willow Run, amid the 3.5 million square feet of production space and the mile-long assembly line, a young woman with a flashlight continued examining tubing, marking defects with chalk, and watching as the components she rejected piled higher each day. The problem was metallurgical, though it took weeks for Ford's engineers to fully understand it. Aluminum and steel are fundamentally different materials with different properties, and those differences matter profoundly when forming metal under pressure. Steel, particularly the tool steel used in automotive dies, has a Rockwell hardness of approximately 58 to 62 on the C scale. It can withstand tremendous compressive forces without deforming. When a steel die stamps sheet steel in automotive production, both materials are hard enough that the die creates a clean forming action. The die doesn't scratch or gouge the steel sheet because both materials have similar hardness characteristics. The stamped parts emerge with clean surfaces, precise dimensions, and no damage to the metal structure. Aluminum alloy 2024 T3, the primary structural material in the B-24 Liberator, has a Rockwell hardness of approximately 60 to 70 on the B scale, which converts to roughly 10 to 15 on the C scale. The difference isn't subtle. Aluminum is dramatically softer than tool steel. When a hard steel die stamps aluminum sheet under the same pressures used for steel automotive parts, the die doesn't just form the aluminum. It scores it, scratches it, and creates microscopic tears in the metal surface. Ford's engineers had designed the dies based on automotive production parameters. The stamping pressures were calibrated for steel. The die surfaces, while polished, were hard enough to cut into soft aluminum rather than merely shaping it. The forming speed, optimized for steel's properties, was too aggressive for aluminum's different characteristics. Every time a die struck aluminum sheet, it imparted some damage. Multiply that by thousands of parts per day, and the defect rate climbed rapidly. The scratches and gouges weren't merely cosmetic. In aircraft structures subject to tremendous stress, surface damage creates stress concentration points where cracks can initiate. An aircraft undergoes constant vibration, temperature cycling, and loading that far exceeds anything experienced by an automobile. The airframe must withstand these stresses for hundreds of hours of flight operation. Surface damage that would be inconsequential in a car fender becomes critical in an aircraft wing spar or fuselage frame. The scratches reduced the metal's fatigue life, compromised its structural integrity, and created potential failure points. The metallurgical laboratories at Willow Run examined the damaged components under microscopes. They could see the scoring patterns clearly. The scratches ran in consistent directions, matching the die movement during stamping. Some gouges penetrated deep enough to remove measurable material. The metal surrounding the damage showed signs of work hardening where the die had compressed it excessively. In the most severe cases, the aluminum showed evidence of galling, where the harder steel had actually torn microscopic particles from the softer aluminum surface. Quality control protocols required inspectors to examine components at multiple stages of production. For critical structural elements, every part underwent visual inspection under adequate lighting. Tubing received internal inspection using small flashlights or specialized optical equipment to detect interior defects. Major assemblies were checked for dimensional accuracy using precision measurement tools. The acceptance criteria were strict because aircraft safety demanded it. Unlike automotive production, where a certain defect rate could be tolerated and corrected through warranty repairs, aircraft defects could prove catastrophic. The inspection records told a troubling story. In November 1941, as production ramped up, inspectors rejected approximately 8% of stamped aluminum components for surface damage. By December, the rejection rate had climbed to 12%. In January 1942, it reached 15%. The rejected parts had to be either reworked, if possible, or scrapped entirely. Rework was labor-intensive and didn't always restore the component to full specification. Scrapping meant wasted material, wasted labor, and production delays while replacement parts were manufactured. Production supervisors pressured inspectors to accept marginal components. The plant was under enormous pressure to meet delivery targets. Every rejected part delayed bomber completion. But Army Air Force's inspectors maintained their standards. They understood that scratched aluminum wasn't acceptable in combat aircraft. They had seen what happened when structural components failed under stress. Aircraft broke apart in flight. Crews died. The standards existed for good reasons, and the Army wouldn't compromise them regardless of production pressures. Charles Sorensen reviewed the defect reports with growing concern. The rejection rates weren't decreasing as workers gained experience. They were increasing. That suggested the problem wasn't worker error or insufficient training. It was systemic. Something fundamental in the production process was causing consistent damage to aluminum components. Sorensen ordered a comprehensive investigation. Teams of engineers examined every stage of the stamping process. They measured die clearances, stamping pressures, forming speeds, and material properties. They tested different lubricants to see if better lubrication could protect the aluminum. They tried reducing stamping pressures, though that risked incomplete forming. They experimented with die surface treatments to make the steel less abrasive. Nothing worked consistently. The hard steel dies kept damaging the soft aluminum. The breakthrough came when engineers compared Ford's dies to those used by Consolidated Aircraft in San Diego. Consolidated used dies made from softer materials, including Kirksite, a zinc aluminum alloy with much lower hardness than tool steel. These softer dies wore out faster than steel dies, requiring more frequent replacement. They couldn't handle the high production volumes Ford planned. But they didn't damage aluminum. The softer die material formed the aluminum without scoring or gouging it. The surface finish on Consolidated stamped parts was clean, without the scratches plaguing Willow Run's production. The implications were devastating. Ford's entire tooling strategy for the B-24 was based on hard steel dies designed for automotive production. The company had invested millions of dollars in die design, die manufacturing, and die installation. Thousands of dies were in production or in inventory, ready for use. Die shops were manufacturing more constantly to support anticipated production increases. The dies represented one of Ford's largest investments in the Willow Run project, second only to the building itself. And they were fundamentally wrong for aircraft production. Changing to softer dies meant more than just buying different material. It meant completely redesigning the stamping process. Softer dies required different press settings, different forming sequences, different maintenance schedules. The dies would wear out faster, requiring frequent replacement. Ford would need to manufacture replacement dies continuously, increasing cost and complexity. The production schedule, already behind target, would face further delays while new dies were designed, manufactured, tested, and installed. The hard steel dies that had seemed like Ford's competitive advantage, the application of proven automotive technology to aircraft manufacturing, had become the project's greatest liability. Part 5, The Climax of Reality, The Turning Point. Part 1. By September 1942, Willow Run had assembled its first complete B-24 Liberator. It rolled off the mile-long assembly line amid ceremony and celebration, photographed for newspapers across the country. Here was proof that American industry could rise to any challenge. Ford Motor Company, applying its legendary production methods to aircraft manufacturing, had built a heavy bomber. The arsenal of democracy was real. Army Air Force's inspectors arrived to examine the aircraft for acceptance. They came with clipboards, measurement tools, and detailed checklists covering hundreds of inspection points. They examined the airframe structure, control surfaces, hydraulic systems, electrical installations, and fuel lines. They checked dimensions, tested systems, and documented every finding. Their inspection took days, working through the aircraft methodically, section by section. The inspection reports were damning. Scratched aluminum throughout the airframe. Gouged tubing in the fuel system. Surface damage on structural components. Dimensional variations exceeding acceptable tolerances. Incomplete forming on stamped parts where dies hadn't applied sufficient pressure. Poor fit between components that should have been interchangeable. The aircraft met some specifications, but failed others critically. Most troubling were the structural issues. Wing spars showed surface damage. Fuselage frames had scratches in high-stress areas. The problems weren't obvious to casual observation, but they were real and they were serious. The Army rejected the aircraft for combat operations. It could serve as a trainer, operating under less demanding conditions with reduced stress on the airframe. But it wouldn't face enemy fire, wouldn't fly long-range missions over hostile territory, wouldn't carry the bombs and crews that depended on every component functioning flawlessly under extreme conditions. For an aircraft designed as a heavy bomber, being relegated to training status was failure. The second B-24 off the line faced the same inspection, the same rejection. Then the third. The fourth. By the time 56 aircraft had been assembled and inspected in 1942, the pattern was undeniable. Every single bomber failed to meet combat standards. Some had more defects than others, but none were acceptable for the mission they were designed to perform. The Army assigned all 56 to training bases, reconnaissance duties, and transport operations. The combat units in Europe and the Pacific would receive B-24s from other manufacturers. Not from Willow Run. The financial cost was staggering. Each B-24 required approximately 150,000 man-hours to build, using materials worth tens of thousands of dollars. Ford had invested those resources into 56 aircraft that couldn't fulfill their intended purpose. The dies represented an additional investment of millions of dollars. The dies couldn't be salvaged or repurposed. Hard steel dies designed for automotive production had no place in aircraft manufacturing. They would have to be scrapped. All of them. Thousands of dies, representing months of engineering work and manufacturing effort, were worthless for B-24 production. New dies would have to be designed from scratch, using softer materials appropriate for aluminum. The die shops would have to retool entirely. The stamping presses would require recalibration. The assembly fixtures might need modification if the new dies produced parts with slightly different dimensions. The production schedule, already a year behind Charles Sorensen's optimistic projections, would face further delays measured in months. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The press coverage turned savage. Newspapers that had celebrated Willow Run's construction now mocked its failures. Will it run? Became the standard joke. Editorial cartoons depicted the massive factory producing nothing but delays and excuses. Critics who had warned that automobile manufacturers couldn't build aircraft claimed vindication. Aviation industry executives, who had resented Ford's confident entry into their field, privately enjoyed the company's embarrassment while publicly expressing sympathy. Henry Ford, 80 years old and increasingly frail, rarely visited Willow Run anymore. The project's problems weighed heavily on him, though he wouldn't publicly acknowledge failure. Charles Sorensen, who had promised 1 bomber per hour, found his reputation damaged. The man who had built the River Rouge complex, who had revolutionized automotive production, who had been Henry Ford's trusted lieutenant for decades, had overseen a spectacular failure. His confidence in applying automotive methods to aircraft had proven misplaced. Edsel Ford, Henry's son and the company's president, bore the heaviest burden. Edsel understood that Willow Run's problems threatened not just one project but Ford Motor Company's entire war production effort. The government had contracts with Ford for tanks, jeeps, engines, and other military equipment beyond the B-24. If Ford couldn't solve the bomber plant's problems, the government might cancel contracts, redirect work to other manufacturers, or even consider nationalizing the facility. The political pressure was intense. Congressional investigators were asking questions. Military officials wanted answers. The public expected Ford to deliver on its promises. The technical problem was clear: hard steel dies damaged soft aluminum. The solution was equally clear: replace the steel dies with softer dies appropriate for aircraft production. But implementing that solution would take time and money that Ford had already spent. The company faced a choice between admitting total failure and walking away from B-24 production, or committing even more resources to a project that had already consumed millions of dollars while producing 56 unusable combat aircraft. Inside Willow Run, morale suffered. Workers who had been told they were building bombers to win the war now learned their aircraft weren't good enough for combat. The quality inspectors, who had been reporting defects for months, felt vindicated but frustrated that their warnings hadn't prompted earlier action. Engineers who had designed the production processes felt defensive, caught between automotive thinking and aircraft requirements. Supervisors struggled to maintain production momentum while knowing the output was flawed. The 42,000 workers at peak employment represented a massive workforce assembled with great difficulty. Housing shortages around Willow Run meant many workers commuted long distances or lived in temporary shelters. Turnover rates were high as workers left for better conditions elsewhere. Absenteeism plagued production schedules. Labor disputes and wildcat strikes disrupted operations periodically. Managing this workforce while the plant's fundamental production methods were being questioned required steady leadership and clear communication. But the leadership was struggling with the technical crisis, and communication was complicated by the need to maintain confidence while acknowledging serious problems. Part 6, The Climax of Reality, The Turning Point. Part 2. Senator Harry S. Truman arrived at Willow Run in February 1943 with his investigative committee. The senator from Missouri had earned a reputation for tenacious investigation of war production waste and inefficiency. His committee had exposed corruption in military construction projects, identified ineffective weapons procurement, and challenged contractors who failed to deliver promised results. Truman was not easily impressed by corporate explanations or bureaucratic excuses. He wanted facts, accountability, and solutions. The committee tour of Willow Run lasted hours. Truman and his investigators walked the mile-long assembly line, examined production stations, reviewed inspection records, and questioned Ford executives. They saw the massive scale of the operation, the sophisticated tooling, the organized production flow. They also saw the quality control stations where inspectors continued rejecting defective components. They examined the dies that had caused the problems. They reviewed the financial data showing millions of dollars invested in tooling that had to be discarded. Ford executives explained the technical issues. The hard steel dies designed for automotive production had damaged the soft aluminum aircraft components. The company hadn't fully understood the metallurgical differences between steel and aluminum forming. The mistakes had been honest errors based on automotive production experience that didn't translate to aircraft manufacturing. Ford was now redesigning the entire tooling system, replacing steel dies with softer materials, and retraining workers on revised procedures. Production would recover. The problems would be solved. The committee should be patient while Ford corrected its mistakes. Truman listened without sympathy. He had seen too many contractors blame delays on technical difficulties while defending decisions that any competent engineer should have questioned from the start. The senator focused on one question: why had Ford, with no aircraft manufacturing experience, insisted on using automotive production methods over the objections of aviation industry experts? Why had the company ignored warnings from Consolidated Aircraft and other experienced manufacturers that hard steel dies wouldn't work for aluminum? The answer exposed Ford's confidence to its core. The company had believed its manufacturing methods were superior to traditional aircraft production. Ford's engineers had assumed they understood metal forming better than aircraft manufacturers who had been building planes for decades. The company had treated aluminum like a slightly different version of steel, rather than a material requiring fundamentally different approaches. Ford's legendary arrogance, which had driven so many innovations and successes, had blinded it to the limitations of its knowledge. Consolidated Aircraft had warned Ford about the die issue early in the project. Aviation industry experts had cautioned that automotive production methods needed substantial modification for aircraft work. But Ford had dismissed these warnings as protectionism from companies threatened by Ford's superior mass production capabilities. Charles Sorensen had been confident that Ford's methods would revolutionize aircraft manufacturing. He had been spectacularly wrong. Truman's committee issued its report in March 1943. The report was surprisingly balanced. It acknowledged Ford's mistakes but also documented the extraordinary challenges the company faced. Consolidated Aircraft had provided incomplete drawings and specifications, forcing Ford engineers to work from sketches and templates rather than detailed blueprints. The Army Air Forces had demanded constant design changes to the B-24, modifying specifications monthly and sometimes weekly. Each change required retooling, fixture modification, and assembly procedure updates. Ford had built an assembly line designed for standardized production, but the customer kept changing the product. The report criticized Ford's decision to use hard steel dies without adequate testing but noted that aviation industry manufacturers had their own production problems. Consolidated's San Diego plant was producing B-24s far below projected capacity. Douglas Aircraft in Oklahoma struggled with quality issues. North American Aviation, building B-25 bombers, faced similar challenges adapting aircraft designs to mass production. Ford's problems weren't unique, though they were particularly visible given the scale of Willow Run and the publicity surrounding the project. Most importantly, the Truman Committee concluded that Willow Run should continue operating. Nationalizing the facility wouldn't solve the technical problems and would likely make them worse by disrupting management continuity. Ford had the resources, engineering talent, and manufacturing expertise to correct its mistakes. The company needed time, not condemnation. The committee recommended that the Army Air Forces work more cooperatively with Ford to stabilize B-24 design specifications, allowing the assembly line to achieve the production efficiency mass manufacturing required. The report gave Ford the political cover it needed to continue. But it didn't solve the fundamental problems. The dies still needed replacing. The assembly procedures still required modification. The workforce still needed training on corrected methods. And the 56 unusable bombers stood as evidence that confidence, capital, and capacity weren't enough without proper understanding of materials, processes, and requirements. By autumn 1943, the top leadership at Willow Run had changed. Charles Sorensen, who had promised 1 bomber per hour and delivered 56 unfit aircraft in a year, stepped back from day-to-day management. Meade L. Bricker took over operations. Bricker focused on solving problems rather than making promises. He decentralized production, shifting more component manufacturing to other Ford facilities and subcontractors while concentrating Willow Run on final assembly. He worked with Army Air Forces officials to establish stable design specifications and minimize disruptive changes. He authorized the complete retooling program, replacing hard steel dies with appropriate materials for aluminum forming. The new dies went into production. Softer materials, primarily Kirksite alloys, replaced the hard tool steel. The dies wore out faster, as predicted, requiring continuous replacement manufacturing. But they didn't damage aluminum. The stamped parts emerged with clean surfaces, precise dimensions, and no scratches or gouges. Component rejection rates dropped from 15% to under 3%. Assembly quality improved dramatically. The aircraft coming off the Willow Run line in late 1943 met Army Air Force's acceptance standards. Production numbers began climbing. From 56 aircraft in all of 1942, Willow Run built 31 in January 1943, 70 in February, 96 in March, 146 in April. By November 1943, the plant celebrated production of its 1,000th B-24. By April 1944, the plant was producing over 400 bombers per month. The mile-long assembly line finally achieved something approaching Charles Sorensen's original vision, not 1 bomber per hour, but 1 bomber every 63 minutes averaged over continuous operation. The young woman with the flashlight, examining tubing for internal defects, noticed the change. The scratched components that had filled her reject pile for months became rare. The aluminum came through clean now, formed properly, meeting specifications consistently. Her job didn't become easier, inspection still required the same attention to detail, but it became less frustrating. She was examining components that would actually fly in combat, not training aircraft that couldn't meet battle standards. By mid-1944, Willow Run had transformed from Will It Run to the most productive aircraft factory in the world. The plant that had struggled to build 56 unusable bombers in 1942 now produced over 400 combat-ready B-24s per month. The retooling program, though costly and time-consuming, had solved the fundamental problems. Soft dies formed aluminum cleanly. Component rejection rates remained below 3%. Assembly quality met or exceeded Army Air Force's standards. The bombers rolling off the line flew combat missions over Germany, Italy, and the Pacific. The first B-24 variant produced by Willow Run in large numbers that went directly into combat was the B-24H. This version differed from earlier models by incorporating the Emerson Electric A-15 nose turret, which increased defensive firepower against head-on attacks by enemy fighters. The structural changes required to accommodate the nose turret demanded extensive retooling, but Ford's engineers, now experienced with aircraft production, implemented the modifications efficiently. The first B-24HS rolled off the Willow Run line in late June 1943. Production totaled 1,780 B-24H aircraft. When the B-24J variant was introduced in early 1944, all three major Liberator manufacturing plants, consolidated in San Diego, consolidated in Fort Worth, and Ford at Willow Run, converted to this version. The B-24J incorporated a hydraulically driven tail turret and other defensive armament modifications. Willow Run produced its first B-24J in April 1944 and built 1,587 of this variant. The transitions between models, once sources of delay and disruption, now occurred smoothly as Ford's production system matured. The peak production period came in April 1944. That month, employees working 2 9-hour shifts, 6 days per week, produced 453 airplanes in 468 hours. This represented a production rate equal to one finished B-24 Liberator every 63 minutes. Charles Sorensen's brash claim of one plane every hour was no longer an empty boast, though Sorensen himself was no longer at Willow Run to see it achieved. The plant had fulfilled its promise, albeit a year and a half behind schedule and only after scrapping millions of dollars in tooling. The workforce that achieved this production miracle included approximately 12,000 women by summer 1944. They welded, riveted, assembled components, inspected parts, operated machinery, and performed virtually every job in the plant except the heaviest lifting tasks. Many were photographed for publicity purposes, becoming symbols of American women's contribution to the war effort. But they were more than symbols. They were skilled workers who had learned complex manufacturing procedures and maintained the quality standards that combat aircraft demanded. One breakthrough that enabled the production surge was Ford's method for assembling the B-24's center wing section. Consolidated Aircraft had built each wing using temporary jigs that held the structure in place during assembly. Each wing required its own jig, and the process consumed 250 man-hours per wing. Ford created permanent jigs into which wings could be moved in and out by overhead crane. The Ford method required 1 man-hour per wing. This 250-fold efficiency gain exemplified the value Ford's mass production expertise brought to aircraft manufacturing, once the company learned to adapt its methods to aviation requirements rather than simply imposing automotive techniques. The plant achieved this production success while continuously implementing design changes requested by the Army Air Forces. The B-24 went through more modifications during production than any other American warplane. Each change required engineering analysis, fixture updates, parts inventory adjustments, and worker retraining. Ford had initially resisted this constant modification, arguing that mass production required fixed designs. But the war demanded adaptation. Combat experience revealed needed improvements. New equipment became available. Enemy tactics evolved. The B-24 had to evolve with them. Ford learned to modify designs while maintaining production flow, building flexibility into what had been conceived as a rigid assembly line process. Sadly, one of the people most responsible for Willow Run's eventual success did not live to see the plant achieve full production. Edsel Ford, Henry's son and the company's president, passed away on May 26, 1943, at age 49. He succumbed to stomach cancer, but the enormous stress of the B-24 project undoubtedly affected his health. Edsel had defended the Willow Run project through its darkest periods, maintained pressure for solutions when problems mounted, and worked to balance his father's increasingly erratic involvement with the steady management the project required. His death came just as production was beginning to recover, just before the plant would vindicate his faith in the project. By the time Willow Run production ended in June 1945, the plant had built 6,972 complete B-24 Liberators. Additionally, Willow Run produced knockdown kits for 1,893 more aircraft. These kits, consisting of 80% of the parts for a finished B-24, were shipped via tractor-trailers to Douglas Aircraft's plant in Tulsa, Oklahoma, and Consolidated Aircraft's plant in Fort Worth, Texas, for final assembly. Including both complete aircraft and kits, Willow Run contributed to the production of 8,865 B-24 Liberators, nearly half of all the Liberators built during the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.